So let's do a few experiments to try to come up with 3 different postulates to use in our triangle proofs.
First, try this. Put your fingertips together like this. Now, bend the middle fingers together so the first knuckles are touching. Now, try to take your ring fingers apart without moving your other fingers. You won't be able to.
Try this. Take 2 drinking straws. Cut the first one into 3 pieces, one 4 inches, one 3 inches, one 2 inches. Do the same with the second straw so that you have 2 identical sets of 3 pieces. Make a triangle out of each set. Try to make the triangles look different. You won't be able to. If 2 triangles have the same side lengths, they will always be the exact same shape.
This is a key postulate in geometry, the side-side-side, or SSS postulate. So we don't need to match all 6 pairs of sides and angles. It's enough to just match the 3 sides to prove that the 2 triangles are congruent.
Side, side, side postulate.
Side, side, side postulate. If 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. The side, side, side postulate.
Let's try an example where we can put the side, side, side postulate to good use. This isn't a theorem we're proving, just a specific problem that you might find on a test. We'll use a proof table to work it out.
Given triangle QRS, with M as the midpoint of RS and QR congruent to QS, prove that triangle QRM is congruent to triangle QSM.
Note that we are not given the information that QM is the bisector of angle Q.
Let's set up our proof table. Our first step is to put down all of our given information. M is the midpoint of RS, and segments QR and QS are congruent.
Our second step is to state that segments RM and MS are congruent. That's the definition of a midpoint.
So, now we've got 2 pairs of sides congruent. The pair we're given, QR and QS, and the 2 that are divided by the midpoint, RM and MS. The only side left is QM, which is easy to prove. Because it's shared by both triangles, we just state that QM is congruent to itself by using the reflexive property.
Now that we've got all 3 sides congruent, we can state our goal. Triangle QRM is congruent to triangle QSM, thanks to the side, side, side postulate.
Pretty simple, huh? We've just used the side, side, side postulate to prove that 2 triangles are congruent. Now, let's take a look at the side angle side postulate.
We'll start with another experiment. Get a friend, 2 rulers, 2 protractors, 2 sheets of paper, a baseball, a glove, and a bat.
Pick 2 side lengths and 1 angle measure. Let's say the sides measure 4 inches and 7 inches, and the angle is 82 degrees. Now both of you draw triangles which have a 4-inch side, a 7-inch side, and an angle of 82 degrees between them. Your triangles should look the same. This illustrates another important postulate of geometry, the side angle side, or SAS postulate. Good job. Now go play baseball.
The side angle side postulate.
The side angle side postulate. If 2 sides and the included angle of one triangle are congruent to 2 sides and the included angle of another triangle, then the triangles are congruent. The side angle side postulate.
Here we have 2 triangles that resemble the last pair. In fact, they went to high school together and ran in the same social circles. We'll use the side angle side postulate to prove they're congruent. What we need to do is prove that they have 2 congruent corresponding sides and 1 congruent angle in between. Given that AB is congruent to BC and BD is congruent to BE, we'll show that triangles BAD and BCE are congruent.
Let's get started by stating our given information. Segment AB is congruent to segment BC, and segment BD is congruent to segment BE.
So, we have been given 2 pairs of sides. To use the side angle side postulate, all we need to prove is that the angles between the sides, angle 1 and angle 2, are congruent. And we notice that angle 1 and angle 2 are vertical angles. Remember the definition of vertical angles? Vertical angles occur opposite each other when 2 lines intersect. And vertical angles are congruent. So, we can state that angle 1 is congruent to angle 2 because of the definition of vertical angles.
So, for triangles BAD and BCE, we have two sides and their included angles. We complete our proof by stating that triangle BAD is congruent to triangle BCE. Our reason is the side angle side, or SAS postulate. We're done!
Let's try one last experiment. With a friend of yours, agree on two angle measurements. Remember, they can't both be 90 degrees or greater, and one side length. Now draw a triangle starting with an agreed-upon side length and putting the agreed-upon angles at each end of the side. Say that you start with a 36-inch side. Put a 40-degree angle on one end and a 60-degree angle on the other. Now complete the triangles. Once again, your triangles should look identical. We have illustrated the following important postulate of geometry, the angle-side-angle, or ASA postulate.
Angle-side-angle postulate.
Angle-side-angle postulate. If two angles and the included side of one triangle are congruent to two corresponding angles and the included side of another triangle, then the triangles are congruent. The angle-side-angle postulate.
Let's look at the triangles here, ABC and EDC. Let's prove them congruent. Sound good? Great! Let's state our given information. We're given that AB and DE are parallel to one another and their lengths are congruent. We want to prove the triangles are congruent using the angle-side-angle postulate.
Let's get started by stating our given information. Lines AB and DE are parallel, and AB and DE are congruent.
Remember the alternate interior angles theorem? Lines are parallel if and only if alternate interior angles are congruent. Well, we'll use it for our reason in step 2. It lets us state that angles A and E and angles B and D are congruent to each other.
So, for each triangle we have a corresponding side, and two angles at its ends. By using the angle-side-angle postulate, we can set triangle ABC congruent to triangle EDC. Our goal is accomplished.
Now that we have some ways to prove congruent triangles, let's move on to using congruent triangles.
Section C. Using congruent triangles.
In the last section, we learned how to use three postulates that prove two triangles congruent. In this section, we'll also want to conclude that a particular pair of angles or segments are also congruent. We can do this because of CP-CTC, or corresponding parts of congruent triangles are congruent. Let's start with a parallelogram, which is a four-sided polygon that has two pairs of parallel congruent sides.
Here we have parallelogram ABCD, which is cut by segment BD, making two triangles, BAD and DCB. We're given that segment AB is congruent to segment CD, and segment AD is congruent to segment BC. And we want to prove that angles 1 and 2 are congruent.
Do you see how we'll do this? We'll prove the triangles are congruent to one another. Then we'll use CP-CTC to prove that corresponding angles 1 and 2 are congruent.
Let's start by stating our given information. AB is congruent to CD, and AD is congruent to BC. We have two pairs of corresponding sides, and we can get the third pair easily. With the reflexive property, we can state that the side shared by both triangles, BD, is congruent to itself. Now we have three corresponding sides.
With these three pairs of congruent corresponding sides, we can use the side-side-side postulate to conclude that triangles ABD and CDB are congruent. Because angles 1 and 2 correspond, our last step is to state that they're congruent because of CP-CTC. Corresponding parts of congruent triangles are congruent.
So, our good friend CP-CTC is pretty helpful once we establish that two triangles are congruent, because then there are all kinds of things we can establish as congruent. Sometimes we can even determine that a pair of lines are parallel by the CP-CTC method. Think about it. If we prove congruent triangles, then we've also proven congruent angles. If these angles happen to be corresponding or alternate interior angles, then the lines must be parallel. Make sense? Let's prove it.
Here's our pair of triangles. Given that LN is congruent to NQ and MN is congruent to NP, we'll prove that LM is parallel to PQ.
First, we'll state our given information. LN is congruent to NQ, and MN is congruent to NP.
Second, we know that angle 1 is congruent to angle 2 because vertical angles are congruent.
Now we have two pairs of sides and a pair of angles established as congruent. So we can say that triangle LMN is congruent to triangle QPN because of the side-angle-side postulate. We've got congruent triangles.
Because we have congruent triangles, we know angle 3 is congruent to angle 4 because of our good friend CPCTC.
Finally, because angle 3 and angle 4 are alternate interior angles, we can state that LM is parallel to PQ. The reason is the alternate interior angles theorem, and we've proven our point.
There are three ways to describe triangles by their sides: equilateral with 3 congruent sides, isosceles with 2 congruent sides, and scalene with no congruent sides. We have 4 ways to describe triangles by their angles. If they have 3 congruent angles, they're equiangular. If they have 3 acute angles, they're acute triangles. If they have 1 right angle, they're right triangles. If they have 1 obtuse angle, they're obtuse triangles.
Corresponding parts of congruent triangles are congruent. This is also known as CPCTC. We can also prove the congruence of triangles with the side-side-side postulate, the side-angle-side postulate, and the angle-side-angle postulate.
What do you call a triangle with sides that are all the same length? You call it an equilateral triangle. An equilateral triangle is also an equiangular triangle because its angles are all equal to one another. Each angle equals 60 degrees.